Welcome back to the deep dive. Today we're shifting gears pretty significantly.
We really are.
Yeah, we are moving away from the high-level strategy stuff. The initial exploration is done, and we are walking right into the engine room of AI project
The
management.
messy part.
Right. We are tackling phase 3 of the PMI CPM AI framework, data preparation.
Yes.
And I have to say, looking at the source material we have today, the study guide, the framework definitions, and this massive corrected question bank, the whole mood of the project really changes here.
It absolutely does change.
Yeah.
I often tell the teams I coach that phase I is about the dream,
Yeah.
understanding the business problem.
Right. The big picture.
Exactly.
Yeah.
And phase 2 is about the inventory, seeing what data you actually have. But
Yeah.
phase 3 is where the data stops being just a concept or a raw resource. It becomes a weapon.
A weapon. That is a pretty intense way to put it.
It is intense, but
Right.
it is accurate. You are taking raw information and transforming it into a format that a machine learning model can actually learn from. You are shaping the ammunition. If you do this wrong, if you prepare the data incorrectly, you are effectively arming your model with bad information. You are building a weapon that is going to backfire the exact moment you try to use it.
And looking at my notes here putting on my working AI project manager hat, it seems like this is the phase where all the skeletons come out of the closet.
Oh, completely. Phase 3 exposes every single assumption your team has made.
Every single one.
Pretty much.
Yeah.
In phase 2, you might look at a messy data set and say, oh, that looks fine. We can probably use that.
And we've all done that.
Right. But in phase 3, when you actually have to select it, clean it, and label it, you realize, wait a minute. We can't explain why we're using this, or this definition doesn't make any sense. It is the put up or shut up phase.
So here's the plan for this deep dive. We are going to treat this session like a high-intensity exam prep.
I love it.
I am going to play the role of the working project manager, maybe a little stressed trying to get the project moving, and you are going to be our exam coach.
The voice of reason.
Exactly. No fluff today. I will give you the scenario, I will give you the options, and then we will do the reveal. But the most important part is the why. We need to understand the mechanics of these failures based strictly on the source material.
Sounds perfect.
Yeah.
And for everyone listening, I want you to play along.
Yes, please do.
This is an active session. When we pose a scenario, commit to an answer in your head before we reveal it. Don't just wait for us to tell you. The real learning happens when you realize why your instinct might have been slightly off.
So we have 3 main task groups to cover today, following the roadmap of phase 3.
Right. We have data selection. This is a high priority task.
The gatekeeper.
Exactly. Deciding what gets in and what stays out. Then we move to data cleansing and enhancement.
Which is also high priority, right?
Yes, high priority. And there's a very strict sequence there that we're going to drill into. You have to clean before you augment.
Got it. And finally, the big one.
Data labeling.
Data labeling.
The only critical priority task in this entire phase.
And that's because it's unique to AI, right?
For good reason, yes.
Yeah.
If you mess up the labeling, you destroy the ground truth. You teach the computer a lie.
All right. I am ready. Let's jump into the first segment, data selection.
Let's do it.
So the task here is select data. On the surface, this sounds pretty straightforward. I need data to build a model, so I go grab the data.
Right.
But looking at the failure modes in the question bank, it seems like the biggest trap is confusing data selection with data quality.
That is the #1 error people make, both on the exam and in real life.
How so?
Well, in phase 2, data understanding, you verified data quality. You asked, is this data broken? Is it accurate? Is it complete?
The inventory check.
But in phase 3, the question changes.
Yeah.
The question isn't, is it good? The question is, why is it here?
It's about rationale.
It is entirely about rationale and documentation. It is about building a defense for your choices.
Okay, let's test this distinction with challenge number 1. This is based on a medium difficulty question from our source bank.
Go for it. Let's hear the scenario.
Picture this. You have a financial services team building a credit scoring model.
High stakes.
Very high stakes. Approving or denying loans, they want to be thorough, so they pull customer records from 4 different databases.
Okay, 4 sources.
Source 1 is current account activity from the last 36 months.
Standard.
Source 2 is historical credit events from the last 10 years.
Also standard.
Source 3 is a legacy collection system, and this thing is ancient. It uses a totally different customer ID format, and it's basically a nightmare to query.
Oh boy. A classic corporate data swamp.
You know it. And source 4 is an external bureau feed that is roughly 6 months out of date relative to the modeling window.
Okay, so we have some messy data in the mix.
Right. And here is the kicker. The team includes all 4 sources in the modeling data set.
All of them.
All of them. Their logic, which they just state verbally in a meeting, is more data is better, so they dump it all in.
More is better. The classic trap.
So here is the question for you and the listener. Which phase 3 task is being misapplied here, and what is the primary problem? I'm going to give you 2 options.
That's here.
Option A, is it a clean data failure? Because they should have cleaned the legacy system and the stale feed before combining them.
Okay.
Or option B, is it a select data failure? Because the team failed to document the rationale for inclusion or exclusion.
Take a moment, listeners. Commit to an answer.
Think about it.
Is it dirty data or is it a bad decision?
Okay, ready. The correct answer is option B. It is a select data failure.
Absolutely it is. And let's unpack why, because option A is very tempting.
It really is. That was my first instinct as a PM. I look at a legacy system with incompatible IDs and a stale feed, and I think, well, that's dirty data. We need to clean it.
Right, you want to jump in and fix the IDs.
Exactly. If the IDs don't match, you fix the IDs. That is cleaning.
But you are jumping the gun. You are
Right.
trying to clean data that shouldn't be there in the first place, or at least shouldn't be there without a very good reason.
Okay, so the dirty data isn't the actual failure here.
No, the failure isn't that the data is incompatible or dirty. The failure is that the team didn't document why they included a 6-month-old feed.
I see.
They didn't document why they didn't exclude the legacy system that clearly has massive linkage risks.
So the failure happens before you even open the file to clean it.
Exactly. The source material talks about this specific concept. It creates an explainability and reproducibility gap.
Explainability and reproducibility gap.
Yes, imagine a regulator comes in 2 years later.
Oh, that's never a fun meeting.
Never. And they look at this model that's denying loans, and they ask, why did you use this bureau feed that was 6 months old? It made the model inaccurate for recently joined customers.
And nobody can explain it.
Right. If your answer is, well, we just thought more data was better, you are in huge trouble.
Because it looked useful is not a valid answer.
It is not a valid answer in professional AI project management. You have to have a defensible reason.
That concept of the gap is really interesting. It's like a gap in the project's memory.
That's a great way to phrase it. If you don't write down the why just disappears the moment the team moves on to the next task.
Yeah.
And specifically, the rules say you need to document rationale for both inclusion and exclusion.
Wait, exclusion too?
Yes.
So if I decide not to use a data set, I have to write a report about it.
You absolutely do.
Yeah.
Let's play out the opposite scenario with that legacy system.
Okay.
Let's say the team decided not to use it because the IDs were just too hard to match. It would take weeks of engineering time.
A very realistic PM decision.
Very realistic. So they quietly drop it. What happens? 6 months later, the model is running in production, and someone from the business side asks, hey, why does the model perform so poorly on customers who've been with us for 15 years?
And those older customers were primarily tracked in the legacy system.
Exactly. And now, nobody remembers why that data is missing.
Because there's no paper trail.
Right. The data engineers don't remember. Is it a bug in the data pipeline? Is it a file transfer error? Or was it a deliberate decision?
You literally can't tell the difference between a bug and a feature.
Exactly. But if you have a select data document that says excluded legacy system due to high risk of ID mismatch and engineering cost, you have an answer.
You have defensibility.
You have defensibility.
So the proper execution of the task here would be to say, we are excluding the legacy system because the IDs are incompatible, and we are writing that down. Or we are including the stale feed because it contains a specific signal we cannot get anywhere else, and we are writing that down.
Precisely. You must document the rationale for inclusion and exclusion before cleansing begins. If you skip that step and just start trying to scrub the data with Python scripts, you have already failed the select data task.
That is a subtle distinction, but I completely see why it matters. It is about the paper trail.
Phase 2 asked, is this data suitable? Phase 3 asks, can you defend why it is in or out? Those are fundamentally different questions.
Okay, I want to keep this moving. Let's go to challenge number 2 in this segment.
Let's hear it.
This one involves what I like to call the informal engineer.
I have worked with many of those.
We all have. This is based on a hard difficulty question in the bank. We have a churn prediction model.
Okay, trying to predict which customers will leave.
Right. The project manager delegates the data selection to the data engineers. The engineers look at the available sources.
Makes sense so far.
They see a legacy system with really bad schemas. Columns are all over the place, data types are mixed, and they also see a real-time feed that looks great.
Okay.
Now, using their instinct, and let's assume they are very smart, experienced engineers, they decide to exclude the legacy system because it looks like a headache.
Which it probably is.
Right, good instinct. And they include the real-time feed because it looks valuable. They do the work, they pull the data, they pass it on, but there's no paper trail, no written rationale.
I see exactly where this is going.
The question for you and the listener is this: is the Phase 3 data selection task complete? Yes or no?
Listeners, lock in your answer. The engineers made the right technical call. They used good judgment. Is the task complete?
The answer is no. It is a
Yes.
failure.
It is absolutely a failure.
And as a PM, I know this is a hard pill to swallow for technical teams because they will argue with you. They will say, but we made the right choice. The legacy system was garbage. Why are you making me fill out forms?
They will argue that all day.
So how do you defend the framework here? Why is it a failure?
You need to write it down because, as the source material strictly points out, instinct is not documentation.
Instinct is not documentation.
A data engineer's technical judgment, if it lives only in their head, creates that exact same explainability gap we just talked about. The exam knows the difference between instinct and rationale, and so does a regulator.
The source mentions a really specific consequence for this undocumented selection scenario. It says, late in Phase V, if someone asks why recently joined customers are missing, nobody knows.
That is the nightmare scenario for a project manager.
Phase V is model evaluation, right?
Right. You are testing the model,
It.
and it is failing on a specific demographic, new customers. The PM asks the team, why aren't there any new customers in the training data?
And the engineers just look at each other.
They look at each other, they scratch their heads, and eventually someone says, oh yeah, I think we excluded that one table last month because the schema was weird.
But nobody wrote it down.
Nobody wrote it down. Now, you cannot reconstruct the decision. The PM is blind.
And here is the real trap of this scenario, looking at the study guide. Coverage gaps created by undocumented Phase 3 selection decisions will look like Phase 2 quality failures in production.
Let's highlight that. That is the exam trap right there.
Can you break that down?
Sure. When the model fails in production because a group of customers missing, your first instinct is going to be, oh, our data quality is bad. We failed Phase 2.
Right. You think the data itself is broken.
But the data wasn't broken. The data existed. You just chose not to use it and didn't document why. So it's not a quality failure. It is a coverage gap caused by a Phase 3 selection failure.
That is incredibly tricky.
It is. It looks like one thing, but it's actually another. That's why the documentation is the only thing that separates a strategic choice from an apparent data quality error.
Wow. Okay. That wraps up data selection. Document your rationale for in and out
Before you clean.
before you clean, which is a perfect segue to our second task group, data cleansing and enhancement.
Now remember the roadmap we laid out at the top. This is a sequence. Step 1, clean data. Step 2, enhance and augment data.
And both of these are high priority tasks.
Correct. Both high priority, and you cannot swap the order.
Why is the order so strict? Why does the exam care if I augment then clean or clean then augment?
Think about the mechanics of it. If you augment data, say, by generating synthetic records to balance your classes, and you do that based on dirty data, you are just multiplying your problems. You're generating synthetic garbage based on real garbage.
You are scaling the errors.
Exactly. You have to clean the foundation before you build the house on top of it. Clean fixes what is broken. Augment adds what is missing. Sequence matters. You can't meaningfully augment data that hasn't been cleaned.
That makes perfect sense. Let's look at a scenario where the cleaning seemed sufficient, but maybe wasn't.
Let's do it.
This is challenge number 1 for this segment. I call this one the hidden nulls.
Hidden nulls.
Yeah.
The silent killers of machine learning models.
Here is the scenario from the question bank. We have an IoT predictive maintenance team.
Okay, so sensors, machines, heavy equipment, lots of time series data.
Exactly. They get their raw data from Phase 2. They do a really solid pass on the obvious stuff. They fix inconsistent timestamps, getting everything synced to UTC. They remove duplicate records. They address out-of-range sensor values.
All standard cleaning tasks.
Right. They format everything nicely so it loads into Python without crashing. The data set is passed forward to the modeling team.
Structurally valid.
Yes, the code runs without errors. But when they train the model, it underperforms severely on one specific type of equipment. Just one equipment model is failing to predict maintenance needs.
Okay.
The question is, which task failed here? Was it a select data failure or a clean data failure?
Listeners, what do you think? The team addressed missing readings, duplicates, timestamps, but the model still fails on one machine type. What task failed?
The reveal. It is a clean data failure.
It is, and specifically a failure regarding systematic nulls.
Okay, Coach, explain that term. Systematic nulls. What is the difference between a systematic null and just a regular missing value?
A regular missing value, a random null, is when a sensor glitches once in a while. You drop a packet over the network. You might have a missing value here and there.
Random noise.
Right. Systematic nulls are when an entire category of data is missing for a specific reason. In this scenario, the source text indicates the team cleaned what they could see.
The formats, the duplicates, exactly. The obvious visual stuff. But they missed that for one specific equipment model, a critical feature column was completely systematically null.
Ah. So maybe that specific older machine model doesn't even have that sensor built into it.
Or it was disconnected for that whole fleet, yes.
But because the team was only looking at structural validity, meaning does the CSV file have the right number of columns and rows, they missed the semantic meaning of those empty fields.
Right. The data set looked full structurally, but for that one machine type, the model was probably seeing a whole column of zeros or blanks if they just did a standard imputation.
So it introduced bias.
Massive bias.
How does that actually break the model, though?
Well, the model learned that for this machine type, that specific temperature feature effectively doesn't exist or is always zero.
Right.
So when it tries to learn a predictive pattern that relies on temperature spiking before a failure, it can't find it for that machine. It just learned a blank space.
The lesson here seems to be that clean data isn't just a syntax check to make the code compile. Correct. Clean data implies addressing all the quality dimensions we established back in Phase 2.
Like completeness.
Exactly. If completeness was a dimension, you had to clean for completeness. You can't just make sure the dates are in the right format and call it a day. You have to look for the things that are missing systematically.
Cleaning must address all problem types, not just the visible ones.
Spot on.
Okay, let's flip to the other side of the sequence. We cleaned, now we enhance. This next challenge is a big one. Augmentation versus leakage.
Oh, this is heavily tested.
And honestly, this one sounds like a mistake I would absolutely make as a PM if I wasn't paying attention.
It's a very common mistake in the industry because it sounds clever, but it is incredibly dangerous.
Here's the scenario. We have an image classification project. Let's say detecting defects on a manufacturing assembly line.
Okay.
The team does two things to improve their data set after cleansing. Activity 1, they realize they have very few examples of a specific minority failure event, a rare defect.
They're very common in manufacturing.
So they generate synthetic examples by taking the rare images they do have and rotating them, cropping them, and flipping them to create more records.
Okay.
Activity 2, a data engineer decides to help the model learn the general trend of defects over time. So they compute a rolling average feature.
Uh-oh.
But they calculate this rolling average across the entire data set, including the test set partition.
I am wincing just hearing that.
The question for the listener is, which of these activities is valid under Phase 3? Is it the synthetic images, the rolling average, or both?
Commit to your answer. One is valid, one is a critical failure.
The reveal. The synthetic images are valid. That is a correct application of enhance and augment data. The rolling averages, that is a critical failure.
Yes. And this is where we dive into the concept of data leakage.
Yeah.
Or specifically violating evaluation integrity.
Break that down for us. Why is calculating a rolling average across the whole data set a bad thing?
It's just math, right? It's just smoothing out a curve.
It is math, but it is math that lets the model cheat on its final exam.
Yes. The test set or the evaluation partition is supposed to represent the future. It is data the model has never seen, held back specifically to test if the model actually learned a pattern or just memorized the answers.
Right, that's basic ML practice.
So if you calculate a rolling average using the whole data set, you are using data points from the future, the test set, to calculate the values of the features at the training set.
Ah, I see. So the training data implicitly contains mathematical information about the test data.
Exactly. You have leaked the future into the past.
Let's use an analogy.
Okay, imagine you are trying to build a model to predict the stock market for Tuesday.
I'd like that model.
We all would. So you want to predict Tuesday based on the last 30 days. If you calculate a weekly average feature And your calculation for that average includes Friday's price, which is in the test set, and you feed that average back into Monday's training data.
Well, the model knows something about Friday's price on Monday.
Exactly. It has the answer key encoded in that average.
It's like studying for a history test, but your textbook has the dates of events that haven't happened yet.
That's a great way to put it. The model will look like an absolute genius during training.
Okay.
It will have 99% accuracy because it effectively has the answer key.
But when you deploy it to production?
When you deploy it to production where the future hasn't happened yet and you can't calculate a future average, it will fail catastrophically.
That is an evaluation integrity violation.
Correct. The source material is very specific about this boundary. You can clean existing records, that's clean. You can add new records like synthetic images, that's augment. But you absolutely cannot use the evaluation partition to compute features for the training partition.
I love the memory hook for this from the notes. You can't augment using the test answers.
It is cheating, plain and simple. And the CPM AI exam will punish you for it if you miss it.
Just to wrap up this segment, I want to reiterate that strict sequence again. Clean, then augment. In the scenario where they generated synthetic images for the rare defects, imagine if they did that before cleaning the data.
Right. Suppose the original defect images had a weird artifact on them, a glitch line across the bottom of the lens.
Okay.
If you start rotating and cropping those images to make thousands of synthetic ones before you clean that artifact, you are now creating thousands of new images with that exact same glitch.
You are scaling the dirt.
You are multiplying the dirt.
Yeah.
So clean the glitch first, then generate the synthetic data based on clean reality.
Clean the foundation, then build the house.
Always.
Okay, well, we are moving fast, but this is great. We have selected our data with written rationale.
Yeah.
We have cleaned it, checking for systematic nulls. We have augmented it without cheating and leaking the test set.
We are doing great.
Now we arrive at the final and definitely the most intensive task of Phase 3, data labeling.
This is the big one. If you are taking the exam, slow down here. Expect this to be heavily tested.
Let's start with a basic question. Why is this the only critical priority task in Phase 3? Selection and cleansing are only high priority.
It's because selection and cleaning are things you do in almost any data project. Business intelligence, traditional analytics, reporting, you always clean data.
Right.
But labeling is unique to AI. It is specific to supervised learning and cognitive models.
Because it creates the ground truth.
Exactly, it creates the ground truth. In traditional programming, humans write the rules to process data. In supervised AI, you feed the data and the labels, and the AI writes the rules.
The data is the code.
The labels are the logic. If your labels are wrong, the model isn't just inaccurate, it is fundamentally learning the wrong thing.
It teaches the wrong pattern with high confidence.
Yes. A label your model can't trust is worse than no label at all.
That is a scary thought for a PM. Let's look at how that disaster actually unfolds in challenge number 1 for this segment. The implicit criteria disaster.
This happens all the time in natural language processing projects.
So we have a team building a sentiment analysis model. They have 50,000 customer reviews to label.
A huge job.
Massive. They define 4 classes for the labelers: positive, negative, neutral, and mixed.
Seems standard on the surface.
Here is the problem. The briefing for the human labeling team is entirely verbal.
Oh no.
Just a quick 15-minute kickoff chat. Hey guys, here are the 4 buckets. Read the reviews, pick a bucket, go for it.
No written guide?
None. No written guide, and no inter-annotator agreement measured.
Disaster.
The result is chaos. Labeler A sees a review that says, great product, but the shipping was terribly slow, and they mark it mixed.
Okay, because it has positive and negative elements.
Right. But labeler B sees a review that says, it was okay, I guess, I don't really care, and they mark that mixed too.
Because they are apathetic and unsure?
Exactly. Similar reviews receive entirely different model scores later because the ground truth is chaotic. What specific element of the label data task was skipped here?
Listeners, think about what was missing from that kickoff meeting.
The reveal. Label data requires 3 things. Labeling criteria defined in advance, consistent annotation guidelines, and inter-annotator agreement measured. They skipped all the documentation.
They did. Let's talk about the phrase implicit criteria.
What does that actually mean?
It means the definition of the label exists only implicitly in the individual labeler's head. It's not explicit on paper.
Like our example.
Right. Labeler A implicitly believes mixed means positive plus negative. Labeler B implicitly believes mixed means hard to tell or neutral.
And the machine learning model cannot read their minds.
It cannot. It just sees the exact same label, mixed applied to two completely opposite types of text sentiment.
So the model gets confused.
It gets worse than confused.
Yeah.
It creates an artificial ceiling on model performance. It does not matter how sophisticated your neural network is. It cannot learn a pattern that fundamentally does not exist in the data.
Because the ground truth is a contradiction?
Exactly. The failure mode here, according to the source, is underdefined criteria discovered post-labeling.
Which means what for the PM?
It means you find out your labels are garbage after you paid for 50,000 of them, which leads to a full relabeling effort before modeling can even begin.
A complete redo. Budget blown.
Budget blown, timeline destroyed.
So to avoid that, the source demands 3 components.
Yes. 1 defined criteria, that's your schema. The 4 buckets,
2 annotation guidelines.
that is the manual. You need a written document that explains the edge cases. What happens when a review is sarcastic? What happens when it's mostly positive but ends with a threat?
You have to document the edge cases.
You have to. And 3, inter-annotator agreement.
Also known as consistency measurement.
Right. You have to actually measure mathematically if people agree with each other when following the manual.
You can't just hand them the manual and assume it works.
Never assume. Which leads us perfectly to challenge number 2 in labeling.
Yes, challenge 2. I call this one the 61% agreement.
This is a great scenario because it's a team that actually did the measurement, but they didn't know what to do with the result.
Okay, here is the setup. We have a computer vision team annotating medical x-rays. They are trying to identify a specific anomaly, so they build a contract risk model. Wait, let me look at the source text. I'm mixing up my examples.
Let's look at the contract risk model example from the bank.
Yes. A team is building an NLP model to evaluate vendor contracts. The classes are high risk, medium risk, and low risk.
Got it. 3 buckets.
They do the right thing and measure the agreement between their human labelers before they label the whole batch.
Good job so far.
Here are the results. For high-risk contracts, the labelers agree 94% of the time.
That is excellent. An A.
But for medium-risk contracts, they only agree 61% of the time.
Ouch. A D minus. Barely better than a coin flip.
The decision point for you as the PM is this. Do you proceed to training? Option A, yes. High risk is the most dangerous stuff anyway, and 94% is great. Let's go.
Okay.
Or option B, no. Stop and take corrective action.
Listeners, you have great data on the really important high-risk stuff. Do you push forward?
The answer is option B. Stop and correct.
This is a critical lesson. Consistency measurement is not a checkbox on a form.
You don't just measure it, shrug, and move on.
Exactly. You don't say, well, we measured it, it was terrible, let's feed it to the AI. If you measure it and it is low, like 61%, you have scientifically verified that your schema is unreliable.
It means nobody actually knows what medium risk means.
Right. If trained human professionals cannot agree on what a medium risk contract looks like, a machine learning algorithm certainly will not be able to figure it out.
The model doesn't know what the labelers argued about in the break room. It just learns the label.
That's a great memory hook. It just learns the label. And if the label is random, it hallucinates a pattern.
So what is the fix here? Do you fire the labelers for being bad at their jobs?
Usually no. The source material prescribes a quality review process.
What does that look like?
You have to go back to component to the guidelines. Maybe the definition of medium risk is too vague. Maybe it overlaps too much with low risk. You have to pull the labelers into a room, look at the contracts they disagreed on, and refine the definitions.
You argue about it, make a decision, and write it down in the manual.
Yes. And then you measure again. You retrain the labelers until that 61% goes up to an acceptable threshold. You simply cannot train an AI on 61% confusion.
I really like how the source material contrasts phase 2 and phase 3 regarding labeling. It clarifies a lot of confusion.
Yes, the cross-phase contrast is heavily tested.
Let's run through that. In phase 2, explore data. You might identify the need for labels.
Right. You look at your data and say, hey, we are building an NLP model to route customer emails. We have the emails, but we don't know what they're about. We need intent labels.
That is defining the cognitive data requirement.
Exactly.
But in phase 3 label data, you actually produce those labels.
One phase sets the requirement, the other fulfills it.
Identifying a labeling need does not equal executing on it.
Phase 2 tells you what kind of labels the AI needs. Phase 3 makes them. That's the distinction the exam wants you to know.
It's like phase 2 is the architect drawing the blueprint. We need a wall right here.
And phase 3 is the bricklayer actually laying the bricks to build the wall. If the bricklayer doesn't have a plumb line, the guidelines, the wall is crooked. It doesn't matter how good the blueprint was.
That brings up a good point about the nature of labeling. A lot of people, especially in traditional tech, think of labeling as just grunt work.
Yes, they do.
Just clicking buttons, outsource it, whatever. But in the CPMAI framework, it seems much more elevated. It's a critical task.
It is elevated because in AI, the paradigm shifts. In traditional software, programmers write the logical rules. If X, then Y.
Right.
In supervised AI, the data is the code. The labels are the logic. So your human labelers are effectively your programmers.
Wow.
If you give them vague instructions, no guidelines, no definitions, you get buggy code. Your model will be full of bugs because the logic it learned was flawed from the start.
The labelers are the programmers. That is a powerful way to frame it for a project team.
It explains why it's critical. You manage it like software engineering with specs, reviews, and quality control.
Okay, we have covered a massive amount of ground today.
We really have.
Selection rationale, cleaning sequence, leakage traps, implicit labeling criteria. Now I want to bring it all together.
Let's do it.
We have one final synthesis challenge from the source. This is based on question 10, kind of the boss level of the Phase 3 bank.
I love synthesis questions. They test if you can hold the whole Phase 3 roadmap in your head at once.
Here's the final scenario. We have an insurance project. The project manager is reviewing the Phase 3 documentation before moving to Phase 3 modeling.
Okay, fine review.
They find 3 specific issues in the logs. I want you and the listener to count how many of these are actual CPMAI framework violations.
Counting mode engaged.
Issue 1. The team used an external partner data feed, but there is no written rationale for why it was included in the final data set.
Okay, that's 1.
Issue 2. The data engineers computed rolling average features across the full data set, which included the evaluation test set.
Okay, noted.
Issue 3. The team finished labeling 10,000 claims, but they never performed a consistency check to see if the annotators actually agreed with each other.
Right.
How many violations do we have? 1, 2, or 3?
Listeners, think back through the 3 task groups we covered. Selection, cleansing and enhancement, and labeling.
The reveal. The answer is 3. All 3 are distinct, critical failures.
It is a hat trick of failure. The project is effectively dead on arrival.
Let's align them to their tasks, just to be totally clear.
Sure. First, the external feed without written rationale. That is a select data violation.
Creating an explainability gap.
Yes. Second, the rolling averages computed on the test set. That is an enhance and augment data violation.
You broke evaluation integrity. Data leakage.
You leaked the future into the past. And third, no consistency check on the labels. That is a label data violation.
Creating a reliability gap.
Exactly. You don't know if your ground truth is real or just a shared hallucination by your labelers.
You know, it's amazing when you list them out like that at the end. It sounds like a project run by amateurs destined to crash and burn.
It does.
But individually, in the heat of the moment during a busy sprint, every single one of those decisions probably felt like a pragmatic shortcut to the PM.
Oh, absolutely.
Just add the feed, we need the data, just run the average across the whole file, it's easier to code, just skip the agreement check, we are a week behind schedule.
And that is exactly why Phase 3 is so dangerous. It is the phase of shortcuts. It is the phase where good enough feels acceptable to a stress team, but good enough fundamentally kills machine learning models.
So as an exam coach, if you had to summarize the entire mission of Phase 3 in one final takeaway for our listeners.
Phase 3 is the bridge between raw data and the model. If you fail here, you don't just get a bad model with low accuracy. You get a model you cannot explain to a regulator, reproduce for an audit, or trust with a business decision.
That is the takeaway. Keep the data clean, keep the rationale written, and keep the labels consistent.
Don't let your team take the shortcuts.
Thank you for guiding us through the minefield today, Coach. This was incredibly valuable.
My pleasure. I hope it helps everyone on the exam and on their projects.
And to our listeners, take a hard look at your current AI project this week. Ask yourself, do I actually have a written rationale for that data set we just pulled in?
If not, you know what to do.
Write one today. We will catch you on the next deep dive.
Stay curious.